rate is set as the duration of control period divided by the duration of observation period. After we get the overall background, we use the number of cases divided by overall background rate to get the patient years. Then use the patient years divided by the observation period to get the required cohort size to generate those number of cases. Yeah, this method. Result. Using Massena's method, give a range of parameters, design parameters with relative incidence set as 2, 5, 10, risk period set as 7 days, 30 days, and 60 days until 1 year, with a fixed observation period set as 2 years. We assume the entire target population during the observation period are exposed, so P equal 1. And with power at 0.8, alpha is 0.05 with one-sided test. The case sample calculation was calculated, and the result shown in this figure. As expected, we see with a relatively longer risk period or with a higher relative incidence, the less some case sample will be required. Here, given we have the number of cases in the estimate in the SCCS study, we will calculate the total cohort size using proposed approach and existing approach, yeah, and compare their results in the setting of the relative incidence as 2 and 2 years of observation period, and the unexposed incidence rate was set as 5 100 person years. So you can see from this table, when the risk period at 7 days and case sample is 919, using the proposed approach, we get the required cohort size is around 9.1 million. Using existing approach, the required cohort size is around 9.2 million, with around 7,000 patients less, which is around 1% decrease in the cohort size. When the risk period is 90 days, for example, and the case sample is 91, using proposed approach, the required cohort size is around 0.81 million. Using existing approach, the required cohort size is around 0.91 million, with around 0.1 million patients less, which is around 11% decrease in the cohort size. If the risk period longer to 1 year and the case sample is 54, using proposed approach, the required cohort size is 0.36. And using existing approach, the required cohort size is 0.54, which is around 0.18 million patients less, which is around 33% decrease. So we can see the cohort size calculated from the proposed approach is always less than that calculated from the existing approach. And with a longer risk period, the difference in the total cohort size between using these two approaches are getting larger. So we did the same test on other parameter settings. Yeah, the result shows in this figure. And from this figure, we can see the similar change pattern. Yeah. So conclusion, testing multiple parameter settings showed that the implement of overall background rate in the SCCS study consistently reduced the required cohort size and compared to the existing approach, which used the unexposed incidence rate only. And the difference in total cohort size can be substantial when a long risk period is required. By considering the background rate of the events in the exposed and unexposed population, fewer patients are required to show the similar effects and more efficient studies can be conducted. Yeah, thank you, everyone. Yeah, this is my presentation. Thank you. I will stop.
Thank you, Ling. While we wait for maybe one question to come in, we'll invite our next speaker, Maurizio Sessa, to go ahead and bring up his slides. And we're going to try to get back on track in terms of our timing. Thank you for everybody being patient during our late start there for a minute. Why don't we just give it one more minute to see if anybody has a question. We see one here. I'm sorry, I don't want to mispronounce your name. A person saying, does the power change if we use this new method? So maybe you can take that question, Ling.
Oh no, we set the power, given the power at point H, then we calculate the number of cases needed. Then based on given the number of cases calculate, then we further to calculate the total number of cohort size needed. So power is not change, does not change. Yeah. Thank you.
Thank you so much. And Maurizio, we can see your slides, so that's great.
Thank you very much, and thank you very much for inviting me as a speaker today. Hello, everyone. I'm Maurizio Sessa, and I'm an assistant professor at the Department of Drug Design and Pharmacology, and I will present today the method known as empirical estimator, which is used to determine the duration of a medication event in secondary data sources that lack information directly or indirectly regarding the duration of the medication event. I have nothing to disclose for this presentation. It's very common in pharmacoepidemiology, many different domains, to have needs for duration of field prescription during the observational window. These range, for example, from studies that want to assess the adherence to a certain medication or the persistence, or rather simply the exposure time, or simply if you want to know if the outcome of interest is occurring during the exposure time. But the question is, what do we know about the duration of this field prescription in the observational window? I've looked a little bit at the pharmacoepidemiological databases that are normally used in pharmacoepi for register-based studies. And I've noticed that this information is in most of these databases not available. And this cannot be indirectly obtained because many times you actually miss information regarding the indication and the dosing regimen. So you cannot indirectly obtain for how long a field prescription is going to last, given the amount of posological unit you redeemed. This means that you need to predict such duration, and there are several available methods out there in the scientific literature, some which use the defining daily dose, some that use the predicted use according to the clinical characteristic of the patients and the expected use for a certain indication. Then we have the waiting time distribution and several others. And now I will talk about a new one, which is the SES empirical estimator. How it works. It's actually very simple. From your source population, you need to preliminarily identify your study population based on your inclusion and exclusion criteria. That's standard practice in pharmacoepidemiology. You will define your observational window for your patients, accounting for censoring. And after that, you will obtain all the redeemed prescription within the observational window. And then we move now to panel B of this figure. What happened next is that you need to identify sequential prescriptions during the observational window at max 2. And as you can see in the bottom of panel B, I've provided 2 examples. Both individuals redeemed 6 prescriptions during the observational window, the gray dot. And but for the patients 1, we will randomly selected only the 5th and the 6th prescriptions, while for the second patients, we will only redeem the 3rd and the 4th. Then we will calculate the number of days between these 2 prescriptions, and this procedure will be done for all the individuals in the study population. Based on these durations, these temporal gaps between sequential prescriptions, we are going to create an empirical cumulative distribution function, which will only include 80% of the distribution. And why we want to do that? Because we don't want to include very long temporal distances that are the natural consequence of stoppers and restarters. Regarding these individuals that we have now identified in our study population, there will be a clustering, which is based on individuals that have similar durations of these sequential prescriptions. And this clustering is done by using machine learning, and in particular, k-means clustering. And there is a special method known as silhouette method that allows, based on properties of Euclidean distance in clusters, to identify the optimal number of clusters for the data we provide to this model. After that, for each cluster, we are gonna take the median of the temporal distances between a randomly selected sequential prescription. And this will represent the median duration for the individuals within that cluster. And this applies to all the other clusters as well. We wanted to assess how good this method was, and we did it using both simulated data and real-world data. We used group-based trajectories to create and simulate 100 individuals with 6 different adherence patterns, individuals that were non-persistent, the group 1, individuals that had a very high adherence in the start, but then they dropped, and these are group 2, partial drop-off. Then individuals that were intermittent, so it means that they alternate period of good adherence with bad adherence, and then individual that had adherence that gradually declined over time, high and medium adherence. And this is based on another, we adapted the simulation from Allermans and colleague that I included the reference at the bottom of this slide. What we have done after, as we simulated our data, we exactly know the real duration of each medication event in the observational window. And therefore, we could compare the absolute difference in days between the predicted duration from the CES empirical estimator and the real duration. And then we took a random date in the observational window for each patient, and we assessed if the individual was correctly classified as exposed or non-exposed based on the comparison between the predicted versus the observed duration. And by doing that, we were able to determine false negative, false positive, true negative, and true positive. After we have done that, we have created a confusion matrix, and we assessed the quality of our prediction. And as you can see, the majority of the metrics we used were over 0.95, which means very good. But the negative predictive value was quite low, and the same applied to kappa. But this was due to unbalance in this matrix. We sampled in order to guarantee balanced confusion matrix, and then both the negative predictive value and the kappa increased. We were not satisfied yet. We want to assess the number of median days of misclassification of duration of exposure, and we found it to be 16 days in all groups. Then we want to assess the method in real-world data. Because we don't have the real duration, we had to use a proxy of true status of exposure. And we used the therapeutic drug monitoring of drugs, which means that individuals underwent to plasma concentration measurement, and the drug was detected in their body. And we then applied the empirical estimated in real-world data on 19 different drugs from different drug class and for different indications, from epilepsy to cardiac arrhythmia. And we assessed the accuracy and the sensitivity of CES empirical estimator in determining the exposure status. And we defined a true positive, an individual that was considered exposed by the CES empirical estimator and had a detectable plasma concentration. And a false negative, an individual that was considered as not exposed, but in reality had a detectable plasma concentration. Based on that, we could calculate the sensitivity. And we found out that sensitivity ranged between 78% to 95.1%, which means very high sensitivity for detecting exposure status. And based on that, we think that this CES empirical estimator is a promising tool to predict the duration of field prescription when this information is not available. Of course, this comes with limitation of the data sources used and the simulation we have performed. But at this stage, that's our consideration. How can you use that? There are tools out there that can be used. We have a Shiny app. I provided the link here, and you can simply upload your data and get the data set with the estimation already provided. And we also have an R package that is available on GitHub that can be downloaded and used. And if you want more technical details, we have a publication out there in which we describe in details the various methods that can be used to determine the duration of pharmacological prescription when you don't have this information. And with this, I want to thank all the people that were directly or indirectly involved in the discussion and the scientific discussion, and to you for listening. Thanks.
Thank you, Maurizio. I'd like to invite everybody, if they have a question, to go ahead and type it in the chat. We probably have time for 1 or 2 questions while we transition speakers. Brad Layton, if you're out there, it'd be great if you're ready with your slides to upload. So we have a question from the audience. Has this method been explored with procedural claims such as chemotherapy that are usually administered at fixed intervals?
No, we couldn't do that because in Denmark, most of the chemotherapy is administered in the hospital, and we don't have access to hospital prescription. So we could not assess many of the chemotherapy, at least those for cancer. Antibiotic chemotherapy, yes, we could do that. But for cancer chemotherapy, no.
Maurizio, I have one other question. In the United States, a lot of times people pick up their next prescription early. So they actually have overlaps where they have medicine supply at home because they're picking up early. Do you have a way to account for that? I saw in the screen, it looked like the prescriptions are sort of all separated, but maybe I misunderstood that.
Yes, we have actually assessed that. I will show you a very simple and interesting consideration for that. When most of these individuals, as you can see, this is the median duration of the redeemed prescription in our cohort over all the individual prescription in the observational window. And as you can see in the start, there is always an anticipation. This means that the median duration in the start is slightly different from the median duration in further episode within the observational window, because of course an individual does want to run out of pills, so anticipate the first, and then this we call it the accumulation or the reservoir. And so what is very interesting, because out of all drugs we tested, this always happened in the very start. So the individuals redeem, get the reservoir, then they don't need to anticipate very much the prescriptions in the later stages because they still have this reservoir. And we have tested the consistency of this estimation. As you can see, if you take a random sequence from the start to the end, you need to be sure that the median duration is equal across the entire observational window. And this is an elegant way to assess that.
Okay, I think we have time for one more question. Is the confusion matrix shown in the slides from the cross-validated predictions?
Yes, we have performed different types of cross-validation. The main issue is that if you want to perform cross-validation in real-world data, which is the final purpose of using this, you don't know the real truth. So the main problem is how you're going to assess the test and the training set, because you can do it on the simulated data, of course, but then when you're going to perform that on the test set with a real classifier, which we don't have, is a little bit complicated. But yes, in the simulated data, we did use it several approach for cross-validation.
Thank you so much, Maurizio. It was very interesting. I'd like to invite Bradley Layton to go ahead and turn on your video and bring up your slides. Bradley is going to be presenting for us the graphical representation of an array of quantitative bias analysis scenarios for differential outcome misclassification.
Hello, thank you so much for having me. Can you see my slides and hear me? Yeah. All right, thank you. So yes, like I was introduced, I'm Bradley Layton from RTI Health Solutions, and on behalf of my co-authors, I'm really pleased to present this work today on quantitative bias analysis. Here are our disclosures. This presentation covers mainly methodological aspects of quantitative bias analysis. We do have an example from an actual safety study that's used for illustrative purposes, but we're not actually discussing any specific exposures or outcomes. So as a little bit of background, identification of clinical outcomes in healthcare databases may be subject to error, as we're all familiar with. And this misclassification of outcome status can bias comparative effect measure estimates, potentially resulting in incorrect study conclusions. Although it would be desirable to confirm each patient's outcome status through formal validation or adjudication, that's typically not possible in every study or in every situation. So quantitative bias analyses are tools that can apply assumptions about the extent of differential outcome misclassification between two treatment groups and estimate a corrected effect measure estimate. Generally, these methods require treatment group specific estimates of the positive predictive value, or PPV, of the outcome. However, treatment group specific PPVs may not be available, and you may only have an overall PPV estimate. So that's the situation we found ourselves in a particular study. And so then this work evaluated how we could use quantitative bias analysis methods to simultaneously assess the potential impact of multiple differential misclassification scenarios on an observed incidence rate ratio, IRR. So to illustrate this point, we used an observed IRR estimate of a hospitalized safety outcome taken from a large new user active comparator cohort study based in administrative claims data. A validation study of the outcome was performed by requesting medical records and review of them by an adjudication committee. But due to a very small number of sampled cases with available medical records in the exposure group, treatment group specific PPVs were not estimated. So we only had an overall PPV. So if we had had individual treatment group specific PPVs, we could have used relatively straightforward quantitative bias analysis methods to correct the observed IRR. These methods account for the different proportion of true cases among the observed cases in each treatment group, and then adjust the IRR accordingly. But in our study, we only had an overall PPV estimate, and the question became how we could use that overall PPV to evaluate our observed results. So we decided to evaluate the full array of all potential differential misclassification scenarios by estimating every possible combination of treatment group specific PPVs. We could then observe how much differential misclassification would be necessary to meaningfully alter our study's conclusions, and then evaluate whether that was reasonable with our observed data. So before we get to the actual results, I'll walk you through a simplified version of our process. We constructed a matrix of all possible combinations of treatment group PPVs in each treatment group, ranging from 0% or complete misclassification to 100% or perfect classification in each treatment group. And on the right, there's the simplified matrix. For example, just showing 10 PPV values for each treatment group. We then used our observed IRR estimate and calculated the corrected IRR estimate at each point of the matrix using the treatment group specific PPVs. In this simplified matrix, we're using a hypothetical example with an observed IRR estimate of 0.8. So you can see that these estimates appear at each point, each intersection on the matrix. And you can see that along this diagonal here, all the corrected estimates are 0.8, the same as the observed IRR. And these are points of non-differential misclassification. However, you can see that at points above the diagonal, all the corrected estimates above the diagonal, the corrected estimates are all higher than the observed. This is because these points correspond to higher PPVs and thus more true cases in the treatment group than the comparator group, moving the observed IRR or the corrected IRR up. However, the opposite is true for points below the diagonal. We then shaded the area of the figure with darker colors corresponding to higher corrected IRR estimates. And we left all corrected IRR estimates below the null as unshaded. This was a safety study with an observed IRR estimate below 1. So our primary concern was to investigate whether there was a truly elevated risk of the outcome, which was obscured by differential misclassification. We weren't necessarily as concerned about the magnitude of IRR values below 1, but the figures certainly could be constructed to accommodate that if it was interest into your study. And so using this figure and the underlying matrix of corrected IRR values, we could estimate numerous useful parameters, such as the possible corrected IRRs in a range of reasonable seeming misclassification scenarios, the worst case differential misclassification scenario given the observed overall PPV and the observed case counts, and the extent of misclassification that would be necessary to substantively change the conclusions of the study. So here's the complete plot using the observed study results and the full matrix of differential misclassification possibilities from our actual study. As in the previous example, the PPV from the treatment group is shown on the vertical axis, and the PPV from the comparator group is shown on the horizontal axis. For readability, the actual numeric corrected IRR estimate values are not displayed on the plot at each intersection, but you can imagine a corrected IRR estimate at each point. However, it's consistent with the example we showed, the darker the shading, the higher the corrected IRR, as we were most focused on just looking at the substantive conclusions rather than the exact magnitude of the IRRs. We then labeled the plot with the observed IRR estimate from our study, which in this case was 0.69, which is shown on the gold diagonal line. Each point along this line corresponded to a corrected IRR value of 0.69, because along the diagonal, the misclassification is assumed to be non-differential. The observed overall PPV estimate, shown here in the gold box, was 56.5% with its 95% confidence interval. And here on the left, you can see the actual case counts from the study. Overall, the study observed 4,505 cases of the outcome in the database. You can see that there's a much larger number of cases in the comparator group than in the treatment group. So if we use the overall PPV estimate of 56.5%, we can assume that 2,545 of the 4,505 observed cases are true cases, as the PPV is the proportion of observed cases which are true positives. And that total number of 2,545, that will come in handy a little later on as we evaluate what level of differential misclassification is reasonable with our observed data. So if we assume that we have an overall PPV of 56.5%, but that it's equal in both treatment groups, and the misclassification is non-differential, then we would assume that the observed IRR is the true IRR, shown here in the intersection of the red lines. However, if we investigate various combinations of differential misclassification, we can see that for treatment group PPVs of 50 to 70%, we would need the comparator group PPVs to be about 20% lower for the corrected IRR value to be 1, indicating a null result instead of the observed decreased result. If we were more concerned about what level of misclassification would be necessary to mask a truly meaningfully elevated IRR estimate, here for illustrative purposes being an IRR value of at least 1.5, the difference between the treatment and comparator group PPV values would need to be even higher, somewhere between 30 and 40%. Now, these levels of misclassification certainly may be possible in some scenarios. However, we were led to ask if these combinations of PPV values were even possible given our observed overall PPV and case counts. And as I mentioned before, using the overall PPV of 56.5% and the 4,505 observed cases from the study, we would assume that 2,545 observed cases were true. Now, given this info, how badly could misclassification have affected our study conclusions? So what if the treatment group had a PPV of 100%, if it was perfectly classified? There were only 190 observed cases in the treatment group. And if all 190 were true cases, then that would leave 2,355 true cases in the comparator group. Having 2,355 true cases out of the 4,315 observed cases in comparator gives us a comparator PPV of 55%. So plotting this combination of 100% in the treatment group and 55% in the comparator group results at this intersection here in a corrected IRR estimate of 1.23. So this represents the worst case scenario under this particular set of assumptions. Because the treatment group is so much smaller than the comparator group, we can see that there's really very little room for the comparator PPV to vary. So almost all of the possible PPV combinations result in corrected values below 1, shown along the red line here. And in the absolute worst case, most extreme differential misclassification scenario, which seems pretty unlikely, it resulted in an IRR of 1.23. So these results were generally reassuring that in our particular setting and study, there wasn't a large increased risk of the outcome, which was being obscured by differential misclassification. Now, in this example, the treatment and comparator medications are very similar drugs used for the same indication, and awareness of or concern about the outcome wasn't expected to differ widely between the two groups. So it didn't seem reasonable that outcome misclassification would vary widely between these groups. However, you can probably think of situations where extreme misclassification could be more likely. So in summary, this plot allows for the estimation and display of multiple possible differential misclassification scenarios simultaneously, rather than just a few selected scenarios. There are limitations to these methods, however. All of these methods require assumptions, which may not be accurate. In this instance, we had an overall PPV estimate of our specific outcome operationalized the way we were doing it in the study, taken in this population and data source. But estimates from external validation studies may not always be generalizable to your target population. Also, importantly, these quantitative bias analysis methods assume that the sensitivity of the outcome algorithm is equal between the treatment groups, and we didn't have the ability to measure that in our current study. And lastly, perhaps one of the bigger limitations in my mind is that all of these parameters are measured with uncertainty and imprecision. And as they're all based on assumptions anyway, I think it's very clear to sometimes use these as proof or fact instead of just kind of supporting evidence. But the variance of these estimates are not easily accounted for in these plots. We're using assumptions about the strength and the prevalence. However, the variance could be accounted for example, using the upper and lower 95% confidence intervals of the IRR or PPV estimates. You could use those to generate corrected IRR values also, but that's really difficult to summarize all of that information in this particular plot. So in conclusion, if you have the very good fortune of having treatment group specific PPV estimates, you can directly use them to correct the observed IRR. But if you don't have them, you can test a variety of different reasonable scenarios which could suggest how sensitive the observed result might be to differential misclassification. Presenting those results on a plot like this may be an easy way to help digest large amounts of information. So thank you so much for your attention, and I'm happy to take any questions.
Thank you, Brad. I don't know if you can see the questions right now in the chat. If they're available to you, it might be easier to read one of them. I think you may have actually answered in your summation and your conclusions and your summation limitation slide. But then
I can find those.
If not, I can read it out loud to you.
If you have one, yes, if you're on top of it better than I am.
Sure. So I'm just going to clarify here. It seems that worst case misclassification would include the possibility of false negative errors not captured by PPV. What was your rationale for confining attention to false positive errors captured by PPV? What assumptions did you make about sensitivity, i.e. false negative errors? And I want to just clarify that you might have answered this in your subsequent slides. It was at the middle.
Yeah, so I think so. Yes, we assumed that the sensitivity is equal between the two of them, which obviously, given the situation that we're in most of the time, where we have observed cases and we can, adjudicate those observed cases and get a PPV. That's usually what we're left with most of the time. So yeah, we focused on the PPV in this case and assumed that the sensitivity would be equal between the two treatment groups.
Thank you for that clarification. Another question comes in. Given that the large imbalance in the treatment group sizes here, isn't it fair to assume that the PPV in the comparator group is the actual estimated PPV and then just vary the PPV in the treated group, which seems to be an inverse of what you presented today?
So I think that could be certainly a case, because and that's the reason that we didn't actually estimate in the end, because we took the observed cases, sampled those, and then by the time we ended up with just a handful of cases in the treatment group, which is why we didn't use a treatment group specific PPV. And so I think that's, I've already closed out my slides, but in the one where I showed kind of that worst case scenario, I mean, you can see that, if you assumed that 100% of the treatment group cases were true or 0% of the treatment cases were true, it almost didn't move the dial at all on the comparator group one. So yes, I think in all intents and purposes, that's very correct, that given this large imbalance, the overall PPV essentially is the comparator group one. And so we can vary small ones. And that's where I showed, like, almost along the entire line, the worst case scenario in that situation was a PPV of 1.23, but almost all of the rest of them were below 1.
Thank you for the answer to that question. I think we'll go ahead and since there's no other questions, we'll close out this presentation. And thank you very much for presenting today. And we'll get started on the next.
Thank you.
Yeah, so thank you, Judith. So Judith moderated the first part of this session. I'm Rosa Gini, and I will be the moderator for the second part. So the next presentation is by Mike Du from University of Oxford, and the title is The Performance of Different Confounders, Standardized Mean Difference Balance Criteria in Cardinality Matching for Medical Device Epidemiology, a Simulation Study. Please, Mike. Are you able to share your screen? Yes. Great.
Can you see it? Oh.
Yeah.
Okay. Hi everyone. I'm a DPhil student in Professor Daniel Pareto Alhambra Group from University of Oxford. And the title of my presentation today is The Performance of Different Confounder, Standardized Mean Different Balance Criteria in Cardiology Matching for Medical Device Epidemiology. So for introduction, cardiology matching is a one-to-one matching technique that uses integer programming to found the largest match sample that satisfy a set of predefined criteria. And some recent researchers have shown it can be used to found match sample from real-world data for causal inference and have advantages over methods such as propensity score matching in terms of sample retention for data set with limited overlap between the treatment groups, However, little research have been done on applying cardiology matching for medical device data with a clustered data structure. So in order to use cardiology matching to found a matched sample that is suitable for causal inference, first you have to give the algorithm some balancing criteria you want your matched data set to satisfy. So to set those balancing criteria, first you have to decide on a distance statistics to use. And for example, in our case, for causal inference, normally we would use absolute standardized differences. Then secondly, you have to decide on which confounder to include. So which confounder you want your matched data set to balance on. So this is quite similar to when you specify covariates to include in your propensity score model. But in here, you just have to let the algorithm know you want your matched data set to have balance on these confounders. And then you have to give the balancing criteria for the confounder a maximum limit on the distance statistic that you specify for the balancing criteria. So for example, you might want your matched data set to have a maximum absolute standardized differences of 0.1 for all the confounder. And then the integer programming algorithm will give you the maximum matched sample that satisfy the balancing criteria that you set in the algorithm. So I did a simulation studies on this method for a medical device epidemiology setting. So the aim of this simulation study is to compare the performance of different confounded balance criteria strategy for cardiology matching for estimating treatment effects for medical device epidemiology study with surgeon impacts. So using Monte Carlo simulations, I generated a clustered data set with 500 different surgeons, and each surgeon have 20 different patients nested under. And the data set contained 5 patient level confounder and also 1 surgeon level confounder. Then the outcome and treatment allocation of this data set are binary. Then I tested several different surgeon confounding that confounder effects on outcome scenario in this simulation study. So the balancing criteria strategy that I set for this simulation study is I included all the confounder as a balancing criteria for the cardiology matching part. So both surgeon level confounder and also the patient level confounder. Then the distance statistics that I set to the balancing criteria is the absolute standardized differences. Then I tested several different maximum limit on the balancing criteria on the absolute standardized differences. So the one that I tested is have a maximum limit of 0.01, 0.05, and also 0.1. Then within the simulation study, the treatment effects are estimated using logistic regression model on the matched sample that I found using cardiology matching with the balancing strategy I explained just now. Okay, so now we go over to the results. So these are the relative bias from the simulation study for the different absolute standardized difference limit strategy that I tested. So the 4 graph here each represent a different surgeon confounded odd ratio on outcome. So the main takeaway from these graphs, I would say, is like using a limit of 0.1 or 0.05 give you quite similar results for surgeon odd ratio scenario, an outcome scenario of less than or 1.5 or equal. And then having a tighter limit of like 0.01 as your balancing criteria limit don't really actually improve the relative bias for surgeon odd ratio of 1.5 or less. But when we have a larger surgeon odd ratio on outcome in your data, this isn't the case. You can see having a smaller limit, balancing criteria limit actually offer quite a bit of improvement in terms of relative bias when using cardinality matching to do causal inference. And then these graphs show you the standard error of the simulation study, which tells a very similar story compared to the relative bias graph I just showed you. So with a surgeon odd ratio of 1.5 or less, having a limit of 0.1 or 0.05 give you similar result, and 0.01 don't actually give any improvement, but as soon as the odd ratio for the surgeon confounder is 2.5, having a matching criteria limit of 0.01 actually offer you quite a bit of improvement compared to 0.05 and 0.1. Then for these graphs are the 95% model coverage, so which tell us a very similar story again. So having for surgeon scenario of 1.5 or less, having a balancing criteria of 0.1, 0.05 give you similar result, and 0.01 don't offer much improvement, but for surgeon effects of 2.5 or higher, 0.01 actually performed the best. So for discussion, so I would say, is it important to consider the limit of the balancing criteria and the surgeon effect on outcome when using cardinality matching for causal inference for clustered data in medical device? And from the simulation result, I found no one size fits all. So that means there isn't like a fixed optimal balancing criteria limit that give you the best performance for everything. So what I found is the best, it very depends on the surgeon effect size on outcome. And then I think when you applying this cardinality method, matching method in real world analysis, it's just worth testing several different limits, then decide on the strategy to use as the best strategies varies with your data set. So, and then the limitations from my study is in my simulation study, I assumed the cluster size are fixed for a cluster, but for real world data, this is very unlikely. And I only consider having same criteria, balancing criteria limit for all the confounder, but this algorithm have the flexibility to apply different limit for different confounders. So for example, you could apply like a tighter limit for some of your stronger confounder, then have a looser one for some of your less important confounder. Then I didn't really offer a performance comparison of cardinality matching to the method. So my result here don't really offer you like performance measuring comparing to other methods. So okay, so I want to acknowledge my supervisor and also everyone in the pharmaco and device IP group at University of Oxford. So that's everything for my presentation today, and I'm welcome for any questions. Yeah.
Thank you very much. I see there is one question now. How easy it is to require interactions between covariates to also be subject to the criteria limit if you're worried about them interacting with respect to the outcome?
Yeah, it's very easy to do that in this algorithm. You can just create an interaction term that and put that in as a criteria limit if you believe there's interaction between whatever covariates between like covariates in your data. So the algorithm is flexible on that. And
thank you.
okay.
Michael, does this reply to your question? We have time for one more question. Thanks. Great, Michael. Oh, Xinyu Liu is asking, besides sample size friendly, what other advantages does your proposal have compared to propensity score matching?
And other advantage apart from sample size friendly is like in propensity score matching, you have to build a model to predict the propensity score. But in this method, you're not building any model, so you don't need to worry about like any statistical modeling assumption that you would worried about when building a propensity score model compared to this method. So.
Thank you, Mike. And Xinyu is also, yeah, thanking you. Well, as a mathematician, though I have a comment on your last answer, I mean, propensity score matching enjoys some theoretical properties. So, yeah, so you would see as an advantage the avoiding those assumptions, which, however, yeah, it's curious for me that you make that comment, that you give that answer.
Yeah,
that's. Oh, if we only were in person, I would offer you a coffee and have a discussion on this.
Thank you. Yeah.
Is there any? We have time actually for another question. So if there is no other question, you recommended to try in real world situations to try different set of parameters before choosing, and what would be the criteria you would use to choose?
I would say if you tested, for example, like I did in the simulation study, like a few different maximum limit on the criteria, I would say like in the real data set, you might see some results very close together, then maybe some criteria limit is further apart. So you might want to choose the one that give you like very similar result. So instead of the one that is odd one out. So that would be my advice, but I think I need further research to back this point up.
Yeah.
Yeah.
Well, anyway, it was really very interesting. Thank you very much, Mike. There is another question. We have 1 minute. You need to be very fast. See the presentation by Stephen Johnson et al. On Wednesday evening for a presentation on the reduction. I've lost. On the reduction in bias when using optimization algorithm-based methods instead of propensity score models, in addition to the reduced sample size. So this is an advice to watch out for the presentation by Stephen Johnson on Wednesday. And then what are the computational constraints of the method? Just 30 seconds. What are the computational constraints?
What are the, oh yeah, the algorithms take quite long to run, so you need really powerful computers. So, but for large data set, it can take quite a while. So that might be like a constraint of this method. So,
okay.
Yeah.
So thank you very much, Mike. Jenny Sun, are you on the call? Okay, so Jenny is from the Harvard Medical School and Harvard People Healthcare Institute, is going to present use of linked databases for improved confounding control, considerations for potential selection bias.
Thank you. Hi, everyone. My name is Jenny Sun, and on behalf of my co-authors, I am excited to share our work titled Use of Linked Databases for Improved Confounding Control, Considerations for Potential Selection Bias. Here are our disclosures. I am currently an employee at Pfizer, but all aspects of the work presented today were completed prior to my employment with Pfizer. So as epidemiologists, we have so many different data sources that we could choose to conduct our studies in. This includes insurance claims data, electronic health records, registries, and more. And with all of these great resources at our disposal, why pick just one? Well, we don't have to pick just one. Now that records for the same patient are often available across different data sources, richer patient data can be obtained through data linkage. In pharmacoepi, the process of linking databases is increasingly used to obtain richer covariate data for improved confounding control. I want to begin by defining this scenario in more detail. For a given study, you as an investigator would begin by identifying a data source to create your study cohort within. I'll refer to this data source as the primary database. For example, this might be an insurance claims data set where you plan to create a new user cohort within. Ultimately, this would be where we identify the target population that we want to make inferences about. Then you might be interested in obtaining additional data that is not available in your primary database. For example, there may be confounders that you need for your study that are not available within your primary database, but are available in a different data source. This additional data source will be known as the supplemental database. And patients within the primary database who have been successfully linked to the supplemental data set will be referred to as the linked cohort. Now, if this subset of linked patients is not representative of the original study cohort identified from the primary database, then restricting an analysis to the linked population could introduce bias. So the objective of this study will be to highlight the importance of considering potential selection bias when working with linked data sources, and to demonstrate how available analytic approaches can be used to account for this potential bias. As our application example, we will evaluate the association of antipsychotics and type 2 diabetes in youths. It's well established that youths treated with antipsychotics have about a twofold increased risk of developing type 2 diabetes, and patients with poor metabolic health at baseline may choose an alternative treatment. So a study conducted within a database that does not capture laboratory data may have residual confounding by unmeasured metabolic test results. The primary database for our study was the MarketScan commercial claims database. We used the active comparator new user design, where the exposed group were new users of antipsychotics, and the comparator group was new users of other psychotropic drugs, specifically antidepressants, medications for ADHD, and mood stabilizers. We defined the index date as the date of treatment initiation. then used a 180-day washout period to define the inclusion-exclusion criteria and to assess the baseline covariates. Patients were followed until the outcome of type 2 diabetes, end of enrollment, or the end of available data. The new user cohort designed within the claims database will be our target population of interest. Laboratory data that we want for additional confounder control is unfortunately not available in the MarketScan claims database. So we obtained this additional confounder data for HbA1c, cholesterol, and triglycerides by linking records between the claims database and the MarketScan laboratory database. This linkage was conducted using the de-identified patient enrollment ID number. Therefore, the overlapping population consisted of patients within the claims cohort who also had test results available in the laboratory database. We actually explored two different ways to define the linked population. We defined linked cohort 1 as linked patients with any laboratory data during the study period, and linked cohort 2 as linked patients with any laboratory data during the 180-day covariate assessment period. We anticipate that this linked cohort 2 will be the most commonly used in pharmacoepi studies. We conducted 2 analyses within each of these cohorts. First, as is commonly done in pharmacoepi, we used inverse probability of treatment weights to adjust for baseline confounding, then used weighted pooled logistic regression weighted by IPTW to estimate treatment effects. This approach does not account for any potential selection bias. In the second analysis, we adjusted for both confounding and selection bias. First, we used inverse probability of selection weights to estimate the probability of selection into the linked cohort conditional on measured covariates. This weighting creates a pseudopopulation in which the distribution of measured factors related to selection are expected to be balanced between the full cohort and the respective linked cohort. Then, within this pseudopopulation free of selection bias, we estimated inverse probability of treatment weights to adjust for confounding. Finally, weighted pooled logistic regression, weighted by both IPSW and IPTW, was used to estimate treatment effects. This approach is intended to create internal validity within the target population of interest, which again, in our study, the target population was the full cohort. In our data set, the full cohort consisted of about 300,000 antipsychotic initiators and over 2 million initiators of a comparator drug. But the linked cohorts got progressively smaller, with linked cohort 2 consisting of less than 5% of the patients from the full cohort. Compared to the full cohort, patients within the linked cohorts were slightly older and more likely to have diagnoses of metabolic conditions, with the prevalence increasing as the definition for linked cohort became more restrictive. For example, the prevalence of obesity was 3% in the full cohort, but increased to 7% in linked cohort 2. But for all other measured characteristics, the distribution was similar within the respective linked cohorts compared to the full cohort. And after applying inverse probability of selection weights, all baseline characteristics in linked cohorts 1 and 2 were similar to the full cohort, including for the metabolic conditions, which is great because that's exactly what we wanted. Now I'll walk you through this forest plot of hazard ratios and 95% confidence intervals. The middle panel shows estimates for estimates before confounding adjustment, and the third panel shows estimates that are adjusted for confounding. In the full cohort, the unadjusted association suggested a 3-fold increased hazard of type 2 diabetes among antipsychotic initiators compared to control patients. This magnitude attenuated after controlling for baseline confounders in the claims and the imputed laboratory data. Here are the remaining results for the analysis with no adjustment for selection bias. In the interest of time, I'll focus on the last panel in green that shows the confounding adjusted estimates. We see that with no adjustment for potential selection bias, that the effect estimates in the linked cohorts suggest a different magnitude of association from the full cohort. But after accounting for selection bias through inverse probability of selection weights, here are the estimated treatment effects. We found that the confounding adjusted estimates within linked cohorts 1 and 2 were nearly identical to the point estimates observed in the full cohort after applying inverse probability of selection weights, which once again was our goal. In summary, in our application example, we found that patients within the linked cohorts were not representative of the full cohort, and failure to account for potential selection bias resulted in incorrect point estimates. But applying IPSW resulted in effect estimates comparable to the full original cohort. And even though we only show one application example, we learned a lot about this often overlooked issue of selection bias in linked database studies. Future linked database studies should carefully consider who is being analyzed and explicitly specify the target population of interest. Then identify an appropriate approach to generate unbiased effect estimates for the target population of interest. I want to end by acknowledging the amazing team involved in this project, Darren To, Ray Wong, and Dongdong Lee. And of course, to thank you all for coming and listening today. I have left my email address here, so please let me know if you have any questions, comments, or suggestions.
Thank you very much, Jenny. Everybody is invited to leave their questions on the chat. While there is no question yet, I can jump in with mine. Thank you very much. I love the presentation. So I see that you didn't consider the possibility that your supplemental data would provide useful information for your inclusion or exclusion criteria. Have you considered applying the same method to this possibility too?
So using data only available in the supplemental data set for inclusion exclusion criteria?
For instance, for the indication, that's a typical thing that you only have on, on a subpopulation. So I guess that the same machinery should work.
Yeah, no, that's a great question. And we didn't think about that, mainly because at least over the past couple years, like my understanding was that a lot of times, usually people go through the effort of linking data sources for confounding control. And I don't know if part of that is we have built up enough confidence to include it as an inclusion exclusion criteria. But I think that's a great idea and something to think about more in the future.
Thank you. That's, I will watch out for your work. There is a question now. Wait. Did you fit the IPSW separately for the selected treater and selected comparator, or did you fit it for all of the selected at once?
That's a great question. So we ran the model separately by treatment group.
Thank you very much. So there is a question in the Q&A instead of the chat. Great job, Jenny. How did the effect estimates look when you control for only claims-based data?
That's a great question. They actually look pretty similar from when we included the laboratory data, which was a little surprising because a priori, I thought that they would be stronger confounders. So I guess in hindsight, if I had known in the beginning they would not be strong confounders, we could have avoided this entire exercise. But I think the thing is, as an investigator, you don't know that in the beginning when you're planning your study.
Yeah, thank you. Thank you for this. And how many patients were lost from the primary cohort to the linked cohorts? Was there a very large difference?
Yeah, so I already stopped sharing my screen, but the slides should be available. So I think in the last link cohort, less than 5% of the original full cohort were still there. So a lot of patients were lost through the linkage. So there were huge differences in sample size.
Yeah, I can imagine. And there is another question in the Q&A that's a bit weird. Persons covered by commercial claims do not uniformly have coverage for all laboratory tests. So one person getting a lab test could impact the probability of another enrollee getting tests due to supply and demand. Can we say that the assumption of independence is satisfied in the logistic regression for the IPSW?
I would probably want to ask the person who asked this question to clarify more on how the probability of someone getting a lab test affects someone else's probability of getting a lab test.
Supply and demand, that's what they clarify, so that there will be less
Got it.
tests available because.
Yeah. I mean, these are widely available metabolic test results. I don't really know a situation. I mean, also, I don't know that much. I'm not a provider, but I don't really know a situation where people would want to get metabolic monitoring and not have the supply for it, just because this is a really common lab test. But maybe in the context of COVID, I could see that being the case. And that's something we hadn't really thought about at the time when we were doing this, but great question.
Great, so thanks for this really nice Q&A session. And so we go now to the last, and thank you very much to you, Jenny. So we go to our last presentation, which is a systematic approach towards missing lab data in electronic health records. And this is Janik Weberpals speaking. Please, Janik.
Hello, hi. Can you see my slides and hear me okay?
Yes.
Awesome, thanks. Thanks a lot for having me. My name is Janik Weberpals. I'm a real data scientist at Roche, and I have the pleasure to present a project that was a joint project between the quantitative sciences team at Flatiron Health and Roche Genentech on missing lab data. This is my disclosure. I already mentioned I'm an employee of Roche, and I hold shares in Roche. So for a vast amount of real-world evidence studies, like especially in oncology, lab data are of utmost importance for various reasons. For example, if you want to emulate a target trial, you need to stick as close as possible to a randomized controlled trial protocol, and labs are often in an exclusion criteria specified in such protocols. Also, for example, for safety studies, labs are often used to ascertain outcomes and measure those. Lastly, also for adjusting, for example, as we've just heard, in propensity score models or in prognostic models, labs are of utmost importance. However, in reality, labs in electronic health records data also often exhibit high levels of missingness. And while there have been a lot of methods described in the literature, but more in an isolated fashion, our objective in this research study was to develop a more systematic empirical workflow and diagnostic workflow to provide evidence for certain missingness mechanisms over others, and derive analytical recommendations to address missing data based on those underlying assumptions. And so the proposed systematic workflow would always start with the null hypothesis to explore the possibility of a lab being missing completely at random. And this can be done descriptively, for example, by comparing patient characteristics and standardized mean difference between patients with and without an observed lab. This can also be done in a more formal statistical hypothesis testing fashion, for example, by applying Little's test, which is a chi-square derived global test for missingness completely at random, or Hodling's test, which is a multivariate t-test, which is designed to test missingness completely at random if you're interested at a single variable at a time. If one would fail to reject this null hypothesis, complete case analysis and multiple imputation is usually what is recommended in the literature. In terms of rejection of this null hypothesis, one could do a subsequent step, which would be to investigate the potential missingness being at random. And we know that missingness at random here, the missingness is a function of the observed values that we have in our database. And this means that the missingness should also be predictable based on the observed data. And this we can exploit by, for example, fitting a random forest based classifier model, which would return us an AUC diagnostic. And based on the AUC diagnostic, we would get an idea how predictable the missingness is, and hence how the missingness at random could be the potential underlying missingness mechanism. And then the recommended approach for MAR is multiple imputation. However, it is in some cases not always feasible to determine or to distinguish MAR and missingness not at random. And in this case, or in both cases, we would always recommend going for a sensitivity or quantitative tipping point bias analysis based on the not at random fully conditional specification procedure, which I want to elaborate on in a second. But to test drive this systematic workflow, we conducted a comprehensive pilot study among first-line treated non-small cell lung cancer and multiple myeloma patients with hemoglobin and albumin labs as exemplary labs for this project. And first, we wanted to validate the assumptions of this systematic workflow by sampling 100 data sets of each 1,000 patients who were observed to have complete labs in the 30 days preceding the first line initiation. And to those cohorts, we refer to as complete cohorts. And to that end, we simulated different missingness mechanisms, including missingness completely at random, and not at random. Specific for this study is that we distinguished two different possible scenarios for missingness not at random, which we called MNAR-easy and MNAR-hard, where MNAR-easy was defined as the missingness depending on unobserved covariates, but independent of the true lab value, and MNAR-hard, the missingness depending on the true lab value. And so the results when we applied the AUC diagnostics based on the random forest classification to our simulated missingness mechanisms in the complete cohort suggested that, as expected, AUC values for missingness completely at random clustered around 0.5. So the missingness was not predictable. The same was also observed for MNAR-easy, for which the random forest classifier was not able to predict the missingness after dropping two variables from the data set, which we do to introduce the missingness. And in contrast, there seemed to be a moderate predictability for missingness at random, with AUC values ranging between 0.63 and 0.67, which is plausible due to the missingness being a direct function of observed data. However, we also observed higher AUC values in not only missingness at random, but also in what I just described as MNAR-hard. Comparing the root mean squared error between imputed and the true lab values, we observed that overall the MNAR-hard mechanism was the hardest mechanism to impute labs under. But among all other mechanisms, the same patterns in terms of imputation performance were observed. And generally, the random forest, a random forest-based imputation model and a k-nearest neighbor imputation model performed best from what we observed in both disease areas. But we also observed a good performance of a simple mean imputation approach, which may be an artifact of the approximate normal distribution that we observed in the exemplary labs in the cohorts that we were drawing. And now, after validating our assumptions in the simulation cohort, we aim to showcase the application of this systematic workflow in some real-world cohorts. And to that end, we randomly sampled, again, cohorts of 1,000 patients for each disease and lab combination. But this time, these cohorts represented patients with both observed and missing labs. So starting with the hypothesis that the missingness could be completely at random, there seemed to be a large difference in patient characteristics indicated by standardized mean differences larger than 0.1 for most of the variables. And this was supported by the Hotterling's test statistic, which suggested highly significant differences if we compared 14 variables between patients with and without observed labs. So we rejected missingness completely at random as the underlying mechanism, and we went on to investigate missingness at random by fitting a random forest classifier model to predict the missingness. And here the random forest classifier results suggested a moderate predictability with AUCs that were comparable to the ones that we observed in our validating simulations before providing some evidence for MAR. However, our simulations results also suggested that both MAR and MNAR hard AUC values can be almost equally as high, making it difficult to distinguish between both of those mechanisms in reality if we don't know the underlying ground truth. So hence, in this situation, we'd always recommend to go for quantitative bias analysis and to quantify and investigate how large MNAR hard would need to be to globally meaningfully discard the conclusion of a given research question. And one way to do this is, for example, to perform a not at random fully conditional specification tipping point analysis. And this sensitivity analysis shifts imputations drawn at each iteration of an imputation algorithm under a MAR assumption by a given quantity, which is the sensitivity parameter delta. And this sensitivity parameter can be interpreted as the average difference between the imputed and the observed values of a variable conditional on all remaining variables of the data. And to showcase this kind of sensitivity analysis, we considered an exemplary overall survival analysis in which we request the time to death due to inareason or censoring as a function of the lab value and other observed covariates. And based on empirical knowledge and literature estimates, we knew that, and we expected that a hazard ratio well below 1 for both labs, indicating a protective effect with higher lab values. And so this analysis was shifted then by a range of delta values to estimate the potential departure if the underlying missingness mechanism was truly MNAR. And this is what you can see here on this plot. So this plot displays the resulting hazard ratios under various sensitivity adjustment with delta equals 1, giving the results of an ordinary imputation without any sensitivity adjustment. And overall, we did not observe any change in our global conclusion, not even under extreme departures from MAR on an MNAR assumption, since the higher confidence limit never touched or even crossed the null. And so hence we interpreted that MAR is likely at the underlying missingness mechanism, and that the resulting hemoglobin hazard ratio in this example did not seem to be very sensitive to potential departures under a MNAR assumption. So in conclusion, we developed a systematic approach to diagnosing missing data mechanisms. We validated this in the Flatiron Health HR-derived database. Overall, we observed that random forest and k-nearest neighbor imputation approaches showed the best imputation performance, which is in line with the literature that I've read. And the not at random fully conditional specification sensitivity analysis provided a valuable addition to build confidence around the analytical assumptions in making about why labs are missing. And with that, I want to thank you, and I want to thank all of the authors that were involved in the study.
Thank you very much. Please type your questions in the chat.
No questions?
Yeah.
Okay, so there's a question that I see. How would you recommend to specify the range of delta in the not at random fully conditional specification when imputing missing baseline covariates? Yeah, that's an excellent question, and we were wondering the same. And I think the only way to go about it is really to consult with clinicians who could give advice on what a meaningful range of departure under really an MNAR assumption would be, since this departure from MAR is also, you always have to take into account also the scale of the lab that you're about to investigate.
Thank you, Yannick. have you considered inputting your range of value also using, so have you ever applied or consider applying your methods to the case when you have really multiple populations, each with different, each covered by different databases, like in a multi-database study?
Yeah, so in this study, we've really just explored one, but that is also in scope of like future investigations that we want to have to really also cover other populations, but maybe one specific about the Flatiron Health database. So the data doesn't come only from one site, but from around 280 sites. And so this could, if you want to see it like that, you could also specify or say that in each site is one, or like each site is one study. So we essentially have like pool data from 280 sites, also from 280 studies.
Yeah, which would actually make your method and your presentation somehow really in parallel with the previous.
Yeah.
Somehow. Yeah. So Judith, thank you to remind everybody that the session was recorded and will be available to everyone, to all the attendees of the conference. So is there any other question for Yannick? I don't see any. Oh, no. Okay. So, Judith, I think we can close our session. So, yeah, thank you very much. It was really exciting for me in particular. This is really, these are topics that I find really fascinating, and all of the presentations were somehow speaking with each other. So I'm really glad to have had the opportunity of moderating it.
Thank you, everybody.